Okay, Salam Sejahtera and good morning, guys. Today we will continue a little bit on the topics on the material that we left since last week, which is the ferrous and also non-ferrous metal. So actually, in the market right now, for the metal, actually there are we have many types. For example, like brass, bronze, steel, metal sludge, aluminium, cast iron, and copper. Okay, but it's on the types of the metal is not only limited to this. We will talk about it later on, right? So actually metal, right? Actually metal, it can be classified into a ferrous metal and also non-ferrous metal, right? For the ferrous metal, I believe most of you have already known, for example, like iron and also steel. Is considered as a ferrous material. So ferrous material, for the pure ferrous material, we have ions and also we have ferrous alloy. So what is meant by alloy is combinations of one or two or two or maybe three metals together. For example, like steel. Okay, steel, which is the edge section or eye section that we normally use in the steel structure. Okay, and also we have high speed steel, which is for the cutting tools. Okay, and then meanwhile for the non-ferrous material, we have pure non-ferrous metal, for example, like copper, zinc, lead, gold, aluminum, tin, silver, and also mercury. And for your information, the mercury is the only non-ferrous metal that is liquid at the room of temperature. Okay. Meanwhile, for the non-ferrous alloys, like what we have already mentioned earlier, alloys actually is the combinations of two or more metals together. For example, like brass. Brass actually is the combinations of copper and also zinc. And then we have bronze, which is the combinations or alloying the copper and tin together. And then we have solder, which is lead plus tin. Okay, so some of the properties for the ferrous metal, we know that ferrous metal are the metal which consists mostly iron and a small amount of other material or elements, for example, like carbon. Okay, so we will talk about that later on. So there are two main properties of ferrous metal, which is the first one, it has the tendency to rusting if it is exposed to the moisture. Okay, and then the ferrous metal, the second properties for the ferrous metal is it is a material which can be picked up by magnet. Okay, so these two properties, one is the rusting, okay, rusting, and the second one is magnetic properties. Okay, so typical ferrous metal including like mild steel, cast irons, and also steel. Okay, so we'll talk about this in detail, which is for the iron, steel, and also stainless steel, and what are the applications in the industry. So in the very beginning, since most of the ferrous metal, no matter it is a pure ferrous metal or it is a ferrous alloy, so most of the compositions in this material is actually iron. Okay, so iron is one of the most abundant metallic material in the earth crust, which is about 4 to 5%, and it can be found in the form of ores as oxides, carbonates, silicates, or even sulfates. Okay, and the most important iron bearing materials or iron ores are hematite and also magnetite. So if you look at here, this is hematite and this is magnetite. Okay, and the most commonly used ore is hematite, which is in this oxides, which is ferrous oxides, and then it contains about 70% of the pure iron, and its specific gravity is in the range of 4.5 to 5.3. And so we have already talked about the concept about specific gravity in our previous video, so you can check back our previous video. Okay, so for the productions of the iron, so iron normally is produced in the blast furnace. So the main functions of the blast furnace is to reduce the ore to metal, followed by the separations of the metal from the impurities. So the impurities here is the slag, which we have already been covered, which has already been covered in our previous topics when we talk about the admixtures for the concrete, right? So the iron ore in the form of pellets or in the forms of sinters is charged into the furnace together with coke and limestone. Okay. Then after that, they heat up the things in a very high temperature, and then the molten iron will be produced, which is pig iron. So the mine of ore is crushed into small particles of the size of 25 millimeter approximately, and then these particles are further reduced to a fine powder, which is later converted to the pellets and also sinters. So what actually is pellets or sinters? So actually, there are products which is from a process, which is what we call sintering or pelletizing. Pelletizing. So the sintering is a process of applications of heat that result in the conversions of the fine ore into hard and porous lumps. So they lumps all of these fine particles into a bigger particles, which is ranging from about 10 mm to 50 mm. Okay. Meanwhile, the pelletizing is about similar with sintering. It's a process of forming balls of sizes approximately 10 mm to 20 mm in diameter with the presence of the moisture. Okay, and the additives such as bentonite and also lime. Right. So the main functions of the blast furnace is to reduce the ore to metals, right? So followed by the separations of the metals from the impurities. So in the furnace, just now we have already mentioned that the iron ore, in the forms of pellets or in the form of sinters, is charged into the blast furnace with the additions of coke and limestone, right? So what actually is coke? Coke is carbonaceous solid produced from coal or petroleum. So it is a raw material from the thermal compositions. Okay, when we burn coal, or petroleums, it will result in coke. It will result in coke, and then limestone. Okay, is charged into the blast furnace together with the iron ore and coke in order to act as a flux, and that holds the silica and also alumina impurities of the ore and also the coke. Okay, so later, after we have charged all these materials into our blast furnace, a powerful air blast through the bottoms will raise the temperature, which is sufficiently to burn the coke, melt ions, and also burn off the oxygen. Okay, you still remember just now the hematite actually is from the ferrous oxide. Okay, so this increase in the temperature actually is to release the oxygen. Okay, is to release the parts of the oxygen. So the temperature that require is approximately 1650 degrees Celsius, which is enough to melt the iron. And then the molten iron, which we collect at the bottom of the furnace, where it contain very high carbon content, which is what we call as pig iron. Okay, so this is how the blast furnace looks like. The what we call the productions of iron. Okay, so this is blast furnace. Okay, the ore, limestone, and coke, they are discharged into the blast furnace. Okay, and then the hot air is blown into the furnace. Okay, and then there are two things. Okay, two things will be collected at the bottom here. One is the slag, okay, which is the admixtures that we use in the concrete. Okay, and then also the molten iron, which is the iron with high content of carbon. Okay, so next we have really talked about this in our past review, which non-metallic product. Okay, and then they're consisting as silicates and aluminates of calcium and other bases. Okay, they are produced simultaneously with molten iron, or what we call as pig iron slag, or what we call as ground, what we call GGBFS, which is granulated, ground granulated blast furnace slag. Okay, blast furnace slag. Okay, so that is its name. And then pig iron actually is not a pure iron, like I said, because it is saturated with carbon, which is about 3.5 to 4.5%, which is taken from the coke. And then it's also contains manganese, which is ranging from 0.25 to 1%, and then silicons 1 to 2%, and other materials or impurities. All right, the melting point is about 1,670 degrees Celsius. Right, so for the pure iron, the carbon content is very low. It's very low. It is only ranging about 0.01 to 0.02%. All right, and then silicon also is it, which is less than 0.1. Manganese, the content manganese is also very low. Okay, the melting point is about similar with the pig iron. It is a bit lower, which is 105 degrees Celsius. Tensile strength is about 335 megapascal. Okay, so this is the steel making process. Steel making process. So actually, the steel making process is here, from here to here. Whilst the process in order to get the pig iron is only from here to here. Okay, from here to here. All right, from here to here, which is we discharge all the what we call the ballast, okay, and then the cinders together with the limestone, also coke, get it into the blast furnace, and then from the blast furnace it will produce slag, okay, and also pig iron. Okay, and then the pig iron, for the pig iron, okay, will add with other materials, which is, for example, like the deduction from the iron ores, from the iron ore, and then we add some iron scrap, okay, and then lime, okay, as a flux, okay, and then we burn it further using either open hearth furnace or electric arc furnace, okay, and then it will produce the product that produce from this open hearth or electrical arc furnace is molten steel. Okay, so the molten steel, they will produce the what we call the final products. Okay, right. We will talk about the electrical arc furnace and also open hearth furnace later on. Right. Okay, so the iron products, they normally come in three forms. So the first one is rough iron, steel, and also the last one, cast iron. Okay, so what is the difference between this is that the content of the carbon. So if we look at here for the rough iron, it has the least carbon content. While for steel, it has about 0.25 to 1.7 percent. Okay, and then cast iron has the most carbon, which is about percent. Okay, so depending on the content of the carbon in the steel, it can result in different type of steel. Okay, because it affects the microstructures and properties of the iron product. So based on these different properties and also what we call the microstructure, we categorize the iron into different forms or different category. For example, like rough iron, steel, and also cast iron. Okay, so for the cast iron and rough iron, the properties for the cast iron is in cast iron we have a gray and white color cast iron in general, and then for the gray cast iron, it is free of carbon, but it is weak and soft. Meanwhile, for the white cast iron, it contains carbon, okay, and it is hard and strong. So if you look at here, actually the content of the carbon will result in the iron, which is stronger and also harder. All right. And then meanwhile, for the rough iron, it has less carbon, high degree of purity. Okay, and then it is a low carbon steel. Okay, because it less carbon. Okay, the mechanical properties is about the same as a pure iron. All right, so the rough iron, and because it has less carbon, okay, so the mechanical property is about the same with pure iron, but the ductility, of course, is lower compared to the steel, but it also can be welded like steel, and it has a very good resistance to the corrosion. Okay, so this is the some of the uses of the rough iron in the industry. For example, like the cranes hooks, anchor chains, and also cores for electric motors and also transformer. Okay, so their properties are soft, malleable, okay, and ductile. All right, bend well, either in hot or cold conditions, okay, and then when it's dropped to our floor, it will give a dull nut, okay, give a dull nut. All right, and then 99% of iron plus 1% of impurities, which including the carbons, sulfur, silicon, manganese, and phosphorus, which is only about 1%. All right, melting point is about there, which is 1,600 to 1,700 degrees Celsius, about the same with the other iron material. All right, so another example of applications of rough irons, okay, for example, like the grills, we use rough iron to produce a grill, okay, to make a gate, okay, and so on. Okay, right. So for the ferrous, we continue with the cast iron. For the cast iron, the applications is, for example, like car piston ring, domestic hot water boilers, okay, drain cover grills, and so on. All right. The properties of the cast iron is it is brittle. Okay. What is brittle? Brittle means that material which will fail in a sudden manner, and sometimes it will accompany with what we call explosive manner. Okay, but on the other hand, cast iron is strong in compressions. Okay, and it snaps before it's bent because it is brittle and the ductility is low, and then the drilling is crumbles. During the drilling, it will crumbles easily. Okay, and flings will also produce fine black powder. Okay, so the compositions in the cast iron is about 93% of iron, and then it has a very high content of carbon, which is about 3%. Okay, and then with the additions of sulfur, silicon, manganese, and phosphorus. All right, melting point is a bit lower, which is 1,200 degrees Celsius to 1,400 degrees Celsius. So this is another example of application of cast iron in the industry. All right. All right. So steel, I believe most of you, which is from the who are from the civil engineering backgrounds, are more familiar with this material, which is steel. The I beam, I section, C sections are all made from steel, and even for the reinforced concrete, for our RC, most of the reinforcement, most of the reinforcement are built by using this, which is steel. We call my steel. Okay, steel is the combinations of iron and carbon. Okay, and the carbon content can be ranging from 0.01 to 1%. Okay, and then it has a slightly higher content of this manganese. Okay, and then it has the phosphorus, sulfur, and silicon also. But a total percentage of this material is only less than 0.6%. Okay, and it is produced like what we have already mentioned earlier, from the basic oxygen furnace or open hearth furnace, okay, or electric arc furnace, which we will talk about this later on. So steel alloy, okay, like what we have already mentioned earlier, alloys actually is the additions of other materials in the iron. Okay, we alloy them together. So the alloys are added to molten steel to produce steel of different characteristics. So if you want to produce steel with different color characteristic, we can add other materials. Let's say if you want to change the hardness, we want to improve the hardness, we want to improve the tensile strength or toughness, we can add alloys. So these alloy materials are manganese. Manganese, it will give strength and toughness to the steel. Okay, like just now for the steel, mass steel, it has a very high content of the manganese, which is about 1.6%, and then we add also silicon, which provides strength and hardening properties, and then chromium and nickel for the corrosion resistance, especially for the stainless steel, and then molybdenum to improve the tensile and also the hardening properties. So we add these alloy materials in the molten steel in order to change or alter a little bit of the characteristic or the properties of the steel to make it to make it up to our desired properties. Okay, so for the steel products, normally it can come in three types, depending on its width, length, and also thickness. We can call it bloom, steps, or billets. So example like this, so billets, we have billets, okay, plats, and also we have blooms. So that is the steel product, and here are some of the properties of the iron bearing metals. Like you can see here, the difference between the compositions in terms of the carbon content, silicon, manganese, and the melting point, and the capacity in terms of the tensile strength and also modulus. And you can see the difference here for the pig iron, for the high strength, what we call high carbon steel, and also cast irons, right? All right, for the steel properties, steel properties is usually contain less than 1% of carbon by weight, and then the structural steel has less than 0.25% by the weight of carbon, and then manganese, which is about 1.6%, is the principal alloying element, because if we want to add the strength, we want to add the strength to the steel, and we have to add some manganese. And steel properties, we all of us may have already know that steel have a very good compressive strength. Okay, it is also very good in terms of the tensile strength, in terms of the shear strength and ductility, and also the stiffness. So if you look at this diagram, so this actually is the stress strain diagram of the steel, stress strain diagram of the steel. So normally it would behave like this. We have the proportional, we have the elastic region up to the proportional limit, and then we have the yield stress yield region, we call it yielding. Okay, and then after that we have the strain hardening. Okay, strain hardening, and then we have the strain softening region. Okay, so if you look at here, we have two lines over here. One is from starting from here, right? Node B, C, D, E. Okay, and then another line, which is this line, which is this line. Not B, C, D, E, not B, C, D, E prime. Okay, E prime. So we have two lines here. So comparatively, we simply put, we say this is the A line and then this is B line. We can say that the B line has better ductility compared to the A line. Okay, compared to the airline. How do you say that? That is because after the material has achieved its ultimate stress, has achieved its ultimate stress. So for the material A, it dropped drastically. It dropped drastically, but for the E, it has the ability to maintain the ultimate stress. Okay, even with the increase of the strain. Okay, so that is the condition where we say a material is ductile. So actually ductility of a material is dependent on the ability of a material to attain strength or to maintain the strength after it has reached its ultimate stress or ultimate capacity. Yeah. Okay, so we continue. So this is an example of utilizations of the steel sections, in the constructions of porter frame, okay, and so on. Okay, standard tensile test specimen, we are using coupon. So normally when we test steel or FRP, we have to use this shape of specimen where you have a bigger end. Okay, and why we want to do that and why we want to design the specimen like this is because we need this tensile test specimen to fail at this region, but not at this region where the machine grab our specimens. Okay, so we purposely make it bigger here and then thicker, okay, so that it will not break at the grips. Okay, that's why we can get the result approximately at the middle. Okay, so this is what we call as coupon. Okay, coupon. All right, so this is how it looks like. The test of the broken what we call tensile steel. Okay, so what is the effects of the carbon content? Carbon content in what we call in the steel. It will affect the microstructure and the properties of the steel. With the increase of the carbon content, it will increase the hardness, strength, and abrasion resistance. But at the same time, it can decrease the ductility, okay, ductility, toughness, impact, and also resistance. Okay, and also resistant. So ductility actually is the what we call the main properties that is required when we are designing an earthquake resistant structure. Okay, so we have, as an engineer, we must have our justification whether the structure required strength. eh, Strength is a priority or the ductility is the priority. Okay, so we have to justify that. All right, and the effects of the carbon content, if you look at this diagram, like we have already mentioned earlier, it can increase the tensile strength. Okay, increase the tensile strength with the increase of the carbon content. It can also increase the yield capacity. All right, but on the other hand, it decrease the percentage of elongation, which is an indication for the ductility. Okay, and then the properties of the steels are also greatly affected by three factors. One is the chemical composition, which is the iron, manganese, and also the carbon. Okay, and then whether it is heat treatment or hot work or cold work. Okay, so what is mean by hot work or cold work? So here, hot working actually is the mechanical deformation at temperatures slightly above the transformation's temperature. Okay, so what is mean by transformation temperature? That is the recrystallization temperature. Where recrystallizations, we can say that it is the melting point. Melting point. And then cold working is the mechanical deformation at temperatures below the transformation's temperature. So cold working, cold form, or cold working, or what we call as cold form, increase the strength of properties but decreases the ductility. Okay, and then yield point is a stress at which there is a marked increase in the strength without an increase in the strength. Okay, so if we look at the stress strain point, it's a stress strain curve. So this is what we call as yield point. This is what we call as yield point, which they increase in the strain. Okay, they increase in terms of the strain, but they have no significant increase in terms of the stress. Okay, sorry, this is increase in the stress. Okay, okay, so that is viewpoint. Okay, and then when we are designing, for example, if you want to design a steel structure, you want to use edge sections or eye section. So normally we'll design based on the yield strength of a material, but not as a what we call, but not as a ultimate strength. We are not design the steel section, not using the tensile, but we are designing it using the yield strength of the stress. Okay, right. Continue. So this is the examples of varieties of the steel sections: beam, column. We have C channel, L angle, and then we have T sheet piling, and so on. Right. Okay. Right. And then for the steel product also, like what we have already mentioned earlier, we have steel reinforcement. Steel reinforcement. Steel reinforcement, which we use in combinations with the concrete, in order to make reinforced concrete. Okay, and then sometimes, in the constructions industry right now, we use the combinations of steel sections and also the concrete sections. For example, like this. This is what we call as composite structure, where this is the RC, reinforced concrete, and then we have steel. Okay, combining, where we are using this together, okay, these two material. All right, then continue. This is our lab. This is our lab. So the the crane, gantry can, is also made by steel, and then the truss is also made by steel. Just different section, different shape. Okay, and then the applications of the steel actually is very wide, in the industry. Okay, so rebar is the reinforcement, which is steel made from mild steel. We use mild steel put into the what we call into our concrete, to take up the tension capacity. All right. So for the non-ferrous metal, at what we have already what we have already discussed earlier, we have copper, brass, aluminum, tungsten, leads, and many others. Okay, so non-ferrous metal, they are metals that do not have any iron in them at all. Okay, do not have iron. Do not have iron. Okay, so which means that they are not going to attracted by the magnet, and they will not going to rust when they are exposed to the moisture. Okay, so the example, this is the example of the non-ferrous metal, and then three groups of the non-ferrous metal. The first one is those of greatest industrial importance. So in the industry, and the industrial normally use this non-ferrous metal, which is aluminium, copper, lead, magnesium, nickel, tin, and also zinc. All right, and then also have the second category, which is the antimony, bismuth, cadmium, mercury, and also titanium. All right. Meanwhile, the third category is the category which is important in the alloy steel. For example, like chromium, cobalt, molybdenum, tungsten, and vanadium, which we have already discussed earlier, where we in the making of steel. So the use in the construction for the non-ferrous metal is also for some of them is used for the structural member, and then most of them are used for the non-structural member. Most of them are being used for the non-structural member. For example, like door frame. The example like aluminium. Aluminium is in the form of aluminium oxide. Alumina oxide. So the most common metallic elements in the earth crust. Okay, and then the bauxite, which is this. Is the chip of the mineral used for the extractions of the aluminium. Okay, in the aluminium. So the properties of the aluminium is it has a very good resistance to the atmospheric corrosions. Okay, and then it is lightweight. Okay, it has very good conduct. It is a very good conductor. Okay, it's soft and easy to work with, and it is very ductile. So some of the window frame, okay, in a very large building, you see the glazing bars, and then we have the roofing sheets, okay, structural members, sometimes panel posts. They are mostly made by using the aluminium. Okay, so in these are the examples of using aluminium. Okay, so I think that would be all for the metals. Sorry, for the steel, for the metals now. I think later on, when Dr. Lau take over the class, you will continue the topics on the metal, which is from a perspective of electrical engineering. Okay, so I think that would be all for today. Thank you very much.